So basically, I will talk about the LTAO mode of AOF, which has been offered for science since April 2019. Since then, it's very much used routinely, actually. More than 30% of the news OBs with AO are done in narrow-field mode. So it's quite an important one at the VLT. News is a very demanding instrument. This mode is providing a very high spatial resolution in the visible. To give an example, this is a globular cluster that is observed with news in wide field mode. So with GLAO, with a pretty good resolution for GLAO, 0.4 arcseconds through width of max. When we turn the narrow field mode on, we get this kind of spatial resolution, something that is defeating HST from the ground, better than 50 mass in the visible, and providing in a small square of 7 by 7 arcseconds more than 10,000 resolved objects for each of these points, each of these pixels to get a spectrum with a resolution of 3000. So this is really a machine for observing deep these kind of globular clusters. Another example is that this facility has turned news into a protoplanet finder. So combining spectral resolution and spatial resolution has allowed to find protoplanets recently. What I want to come to is that this mode is very powerful and operational on the bright regime. And now we are trying to improve it on the faint end for extragalactic science. Basically, today we have a limiting magnitude where we reach the expected performance with a stride ratio at 650 nanometer, larger than 5%, and with a goal of 10%, around 14.5. And with this, so we can close the loop until 15. With this, we can address a handful of quasars. This is an example to show the type of extragalactic size that we are missing. And by analytical formula, we could confirm that this is expected, and that by changing our detector, our natural gas hour reference sensor detector, and improving the readout noise from 11 electron to 1, we could gain about 2 magnitudes. And in this case, be able to address a couple of thousand of quasars. So it's very meaningful. Let's say in terms of sky coverage, it's minor. In terms of number of specific targets, it's really spectacular. But in the process, we found that, I mean, our baseline today is to work in 2 by 2 shaka. We found that going full pupil would allow actually to address all of them. In the process, we ran a few end-to-end simulations that were confirming the potential gain of 2 magnitude in 2 by 2. And about 3.5 magnitude in full pupil mode. And so that was the start of an upgrade project to improve the natural gas hour reference sensing for news narrow field mode. And now I want to give you just a few technical highlights. We have finished our MA80 phase. We are ready to commission this upgrade. And here I wanted to say, okay, I have to say this is based the upgrade on the Zafira detector. With sub-electron without noise. However, in our noise budget, we need to care very much about the other terms. And so we need to have a well-controlled budget when it comes to managing the dark level, the thermal background, and the sky background, of course. What do you see? Yes, sorry. So this is the wavelength range. We are operating in J plus H, and basically, above the H band, above 1.8 micron, you see that the black body thermal emission is huge, and so we need to cut it. So we have designed a custom filter to bring that down to the level of the sky, basically, in the integration domain. For that, we need a filter, in our case, with an optical density larger than 5. In the end, we have a pretty balanced budget. I just wanted to insist on that. Yeah, sorry, what I forgot to say is that the Zafira detector has a QE curve that depends on the APD gain, and that is never zero at very far wavelengths. So that this is something to care about. Then, once the system was able to receive photons without too much background, we could optimize the readout mode, so the readout sequence, and play with a quite wide parameter space. And so here a few snapshots. We have tried to optimize the APD gain, so the avalanche amplification factor, and the number of Fowler pairs, because we are in a Fowler sampling regime. And so, as expected, we can get to very low subelectronic readout noise, in this case with a high APD gain of 100 and 4 Fowler pairs, a readout noise of 0.36 electron RMS. This is actually not even readout noise, readout noise plus dark, plus the thermal background from the entrance window of the cryostat. But this is at the cost that you can see here on the right plot of an integration time a bit underwhelming. At 500 Hz, we have a dip of 1.3 milliseconds. And it's quite basic, this coming from the fact that the Fowler sampling reduces the effective integration time with the number of Fowler pairs. So obviously what we want to do is not to minimize the readout noise, is to maximize the SNR. And so for that, we need to combine the readout noise to the background levels. We need to take into account the signal level with the right integration time and with the excess noise factor that depends on the APD. And when we do all of that, we can plot some SNR curves where, in this case, for 500 Hz, around magnitude 16, which is pretty much the end of this mode, we have a sweet spot around APD gain 50 to 70 and a couple of Fowler pairs maximum. So we have done that for all our modes and scanning other parameters than what I show here, and basically baselining them, populating our configuration, and finally doing a few tests to verify that we are getting what we expect. So here on the left, you see slopes noise measured from the lab against flux, and we have the measurements in blue and the expected regime in red for photon noise, yellow for photon noise plus RON, and purple with background noise and background level to explain this plateau. We have this plateau because we didn't want to clip our measurements. We are using just a classical center of gravity without threshold. It's really suboptimal. Our purpose was to verify that it behaves as we expect with standard analytical formulae. So there is room to improve that, of course, and we'll do it on the real system. And the purpose of this curve is to show that, I mean, where we want to operate is above an SNR of 3. Basically, the rule of thumb is that you want to have 10 times more photon than without noise. And in our case, without noise is about 1 when you put everything together. So you want to have 10 times more photon in your PSF core. If you take let's say, a conservative assumption of a Schreier ratio of 50% across J plus H with a wavefront error of 116 nanometer RMS, you want to have twice more photon in your subaperture. So you want to be at 20 photons per subaperture per frame. And there we can see where we end in terms of faint magnitude, where we want to stop doing wavefront sensing. And the summary of this analysis, this rough analysis, is on the right side, where you see that basically we want to deliver a high performance mode, 500 Hz, 2x2, where we very well sample the focus and astigmatism mode and minimize the typical residual and the vibrations up to J magnitude 16, and then switch suddenly to a full pupil mode with 200 Hz to address the faint end up to 18.5 plus, hopefully. These are the two main modes we want to offer for unresolved targets, plus the potential for a high sky coverage mode. The purple curve is an 80 Hz mode. And basically what we are thinking about is to use the telescope field stabilization probe, which is running at this rate, but has a much larger partial field than we do, to have, in principle, a very high sky coverage, or almost 100%. It's not completely true because we still need to address the true sensing in a post-focal manner, and we need to address this point. So this is my last slide. Sorry for being a bit too long. So today, I mean, the message to take home from my perspective, that the use LTAO is routinely used. The upgrade project that I've tried to shortly describe here is in a good shape. The MAIT phase is completed. We are currently going through the PAE review, getting RICSs and answering them. The system is fully baseline and configured. All the modes have been tested. We could even connect the system to RTC here, running with the same software as in parallel. And so, as I showed in the last slide, we want to deliver a high performance mode for bright targets and a very deep mode for the other ones. The next work on our side is to, it's ongoing, actually just started, to work on focal plane wavefront sensing for the full pupil mode with a single PSF to be able to extract low order modes, essentially defocus, but also astigmatism and possibly low wind effect as well, with the idea to address that with machine learning. we are in a good situation in this case because we have a very well sampled PSF. So we are working between 900 nanometer and 1.75 micron. And our pixel scale allows to sample even at the bluest wavelengths. We have NIQUIS sample over the full range. We have the high trail in H band. It's a bit lower in the blue end. It's about 35% at 900 nanometer. But let's say good conditions, diffraction limited core. And we hope to be successful in providing focal plane wavefront sensing to keep the true sensing available in the full pupil mode. And if COVID allows, we hope to commission that and offer it to the community in 2021. Thank you.
Thank you very much, Sylvain. Nice talk. There is a question from Mercy Reddy. What is the value of excess noise factor? Can you count photon in low flux level with high APD gain?
So first question, I think I have a slide in the backup. Do you see that? This excess noise factor slide? Well, basically, to answer the question, the excess noise factor that we have characterized and that we take into account in our analysis is 1.2 at APD gain 100. This is what you see at 90 Kelvin, which is our operating temperature. So it goes from 1 to 1.2 when you raise the APD gain from 1 to 100. This is invariant, so it's not very large. Still, this is enough to make a bit lower APD gain more optimal than 100. Another thing you lose with high APD gain is dynamic range, of course. So when you want to offer a mode of a large dynamic of magnitudes, it's quite important. And the other question is whether we can count photons. I didn't try, but I know that Kurt Finger did with the same detector, exactly the same detector. And he published something about that. I can share the paper later.
Okay, thank you very much. Any other question? Nope. Okay, thank you very much, Sylvain, and thank you to all the speakers of the afternoon. And